Ladies and gentlemen, dear Martin Böfer, first of all, I'm very pleased to be here to speak about some very big Austrian projects which are right now under construction. I'm sorry not to be able to speak in Spanish, but my Spanish is not possible to present something. Can we switch on the beamer? Yeah. I would like to introduce you to three quite big projects. All of them are railway projects. Austria, by the way, has about existing tunnels, 300 of kilometers of railway tunnels and about 300 of kilometers of motorway tunnels. They are running now to get an age of about 100 years, so we are thinking on renovation of these tunnels already. But we are now in the center of Europe, and I will show the axis why we have to build these tunnel projects. First of all, I start with the Brenner-based tunnel. As you might have heard, Europe grows together, and we are building a railway line from Berlin to Naples. This railway line has a length of 2,600 kilometers and lots of tunnels in between. And many or some of these tunnels are also situated in Austria, and the longest of these tunnels is situated between Austria and Italy. And I was listening to your speech. You said you connect Chile with Argentina. You have the great, let's say, advantage that your language, I think, is the same between Chile and Argentina. We have the problem that we build a tunnel between Italy and Austria. And the problem is that we have different languages and different, I have to say, mentalities. Yeah? The mentality of Italians is a little bit different than that of Austrians, and that's why we agreed to write the contract in two languages, so in German and in Italian language. The project itself, here is the city of Innsbruck, which is the main capital city of Tyrol, which is a province of Austria, and has then a length of about 55 kilometers down there to Franzensfeste, which is a small part, a small village in Italy, and then goes to our next tunnel, which is about 20 kilometers long, which is the Tunnel Schalder, after 700 meters coming out. So we're going 55 kilometers in, then for other reasons going out for 700 meters just, and then another 20 kilometers in down to Bolzano, which is in Italy already. Then we connect this tunnel to the existing about 11 kilometer tunnel Intar. So if you go in future from Munich to Italy, you will go through this tube and then bypass down here and then run into the Brenner-based tunnel. So for this reason, this will be, if we count also these sideways to the whole tunnel project, a 65 kilometer long tunnel project. Yesterday we already discussed the distance of the cross passages. As you see, we will build 3 tubes for this tunnel project. There's a yellow line below there because Germany, Italy, Austria are thinking to connect also the electricity from Germany to Italy. And this third tube is for the moment the exploratory gallery, but will then be used for transporting high voltage energy from Germany to Italy or vice versa. So all in all, we build around 200 of kilometers of tunnels in this project. You see that we have so-called multifunctional stations in between, so that if a train gets a problem, it's so to say a main train station underground, and we agreed to a distance of about 20 kilometers in between these ones. The main question was learning from the Gotthard-based tunnel from Switzerland, what is the right distance between the tubes? And we have an even more complicated situation because we have this tunnel down there, which is the exploratory tunnel, and the Gotthard base had just these 2 tubes. And we learned from them they had a distance of about 40 meters, and visiting them very often we saw that they get some problems in the first tube when they come with the second, because the stress is going on the first tube, and they had to repair the first tube by building the second. And that's why we started to make intensive calculations on the topic how far have the tubes to be away from each other, not to get any geotechnical problems. And you see we keep elastic zones in between, and that's why we have now agreed on a distance between the tubes of about 70 meters, with a third tube, the exploratory gallery, which is about 12 meters beneath those two. Will also be used for dewatering the ground, by the way, because there is a lot of water in some sections expected, and we will build this tube first to dewater and then have dry conditions in the main tubes, which will follow afterwards. Typical cross-section is a little bit bigger than we are used to do that in Austria normally, but the European Union specified technical let's say specifications for getting not only the profile. You have to think, in future we want to run the trains from Finland to Greece, or from Germany down to Italy. However, this needs so-called TSI specifications, technical specifications for interoperability. So we have a guideline for the electricity, we have a guideline for the geometry, we have a guideline for everything, so that we have a unique, let's say, design for all the European region, and this is a typical one, so that we can run all the trains within these tunnel tubes. Typical cross-section, one tube, second tube, third tube in between. From the working safety, we have to make these shafts in regular distances. We are a little bit in fight about the use of this third tube, because the Italian fire brigade would like to use this third tube for rescuing, which is not foreseen in reality in the Austrian side, because we will use trains for rescuing out of these situations. We have some situations where the tubes are on different levels, and we are not allowed to make inclined shafts anymore in between there, because the European Union also had foreseen that handicapped people have to get a chance to get out. So we have to make these ramps, as you can see here, so that handicapped people can escape from one tube to the other. And if the inclination would be that high, there would be no chance for the handicapped people. By the way, this made also the cross-section a little bit bigger. I go back to this slide. That's why we now have a sidewalk of 120. In earlier days, the older tunnels have a sidewalk of 60 centimeters. Now we have 120, which means all the older tunnels have to be renovated, because escaping on this width will be possible, but on a 60 centimeter sideway will not be possible. And on the other side, we have a way for the maintenance guys, which is a little bit more narrow, as you can see. Then this typical multifunctional station layout, as you can see, the tunnel tubes are quite big there. This is a bus. We did not provide shafts like the Swiss did at the Gotthard base tunnel. They provided shafts here and there. At the Brenner, we went another way. We said we would like to avoid any shafts, and we would like to have roads in, so that in the escape situation we can bring in buses on three different ways. We were a little bit skeptic if this would work in an emergency case to bring out the people via the shafts. So this is not foreseen. There's no shaft in this all construction. By the way, we have an overburden of about 1,800 meters in the maximum, and doesn't it work? Sorry. 1,800 meters of overburden, and I can hold it. I can hold it. It's no problem. And this is the situation which we have all the 20 kilometers. There's electricity foreseen in here. There are toilets foreseen in here, so that a train can be evacuated in this station. The concept foresees if the buses are not here very quick, it is possible to escape via the other tube. So the second tube is always the safety tube for the first. This is a main concept behind that. Of course, we need some smaller shafts for ventilation. The ventilation buildings are quite big. You see the bus size here. So this is a main issue for maintenance reasons and for fire safety. Therefore, we need this ventilation. I come to the next projects, which are the Semmering-based tunnel and the core arm tunnel. We have a second link going, let's say, from Finland, which is up here, then through Poland, down to the Adriatic area. We would like to connect this area in a new corridor. And as you can see, this corridor passes Austria. And this passing Austria means we have a complete new railway line going from Vienna down to Klagenfurt, which are the main capital cities. This is Carinthia, here's Styria, and here's Vienna. So we have to build a new tunnel here, which is the Semmering-based tunnel, 2 tubes with 27 kilometers length, and the core arm tunnel in this area, 2 tubes, 33 kilometers of length. Why do we do so? To be connected to the harbors. Austria is a country which has no connection to any harbor, which is a big disadvantage from the economy point of view. So we would like to get this connection to the harbors on the northern side and also on the southern side. This will, in our opinion, bring positive effects to the whole region, to the economy, because we have a lot of steel industry in our region. To bring the material by train will be much more easier than afterwards. Then a reduction of the travel time, of course. To go from Vienna to Graz takes you, for the moment, 3.5 hours. In the future, we count on half an hour less. And there is even no connection, train connection between Graz and Klagenfurt. This is a complete new line, which takes you for the moment 3 hours and then will take you 1 hour. So this is a really good reduction for the travel time. Changes in the model split. We would like to bring all the mass on the train. We would like to get rid of the lorries. The problem is the lorries, they destroy our roads in reality. They have 40 tons maximum allowed mass, and we would like to bring them on the train, on the rail. A big issue in Europe is the CO2 production. We always get penalty because we produce too much CO2, and we would like to get a production of less CO2 because of bringing much of the mass transport on the rail. We hope to get less accidents then, connect 3 centers of Austria by these tunnels. Cost of these lines, Semmering and Korm, is about 9.2 billion euros. Together with these new railway lines, we built new main stations. This is the new main station of Vienna, which is already almost ready and full under operation, let's say, end of 2015. And a new main station also in Graz. And we see already that people like these new infrastructures. And if you would like to go by train from Vienna to Salzburg nowadays, where we built already a lot of tunnels, the trains are full of people. In earlier times, nobody wanted to use the train or were going by car, but now this infrastructure is really well used. I start with the Semmering-based tunnel, some details. Length 27 kilometers, as I said. Gradient, by the way, is 0.84. This is the reason why the tunnel gets so long. But here we have a European rule which says we are not allowed to make an inclination more than 0.85 in whole Europe where mass is transported, because the principle of Europe is to save energy. And if we have to climb up such steep, then we need a lot of energy, because the tunnel should work for at least 100 years. And to save energy, all these lines have to be very flat. And the maximum allowed is 0.85, and we do it with 0.84 there. So energy efficiency is a top priority in the European Union. As you see, we have 2 parallel single-track tubes. In earlier times, we put 2 tracks in one single tube, but this time is over from safety reasons, so longer tunnels all get 2 tubes. We have cross passages, a maximum distance of 500 meters has to be done, also a technical specification of the Union. 1 emergency station in the middle, because the tunnel is 27 kilometers long, we need just 1 emergency station. The portal location is in Gloggnitz and Mürzzuschlag, and further access during construction in Göstritz, Fröschnitz and Krautschenhof. I give you an overview of this project in a few seconds. A lot of drills were done, a lot of geological, let's say, exploration. All in all, as you can see, we did 24,000 meters of drills. This is almost the length of the tunnel, but of course the drills have just the 10 centimeters of diameter. But this is what we assume the most difficult project we ever did in Austria, because the geology is, I would say, very, very complex, but we have a geologist with us, so he can tell more about that. More than 1,000 samples were tested in the laboratory, and by the way, the project lasts a long time. The first approval was given in 1989. And then we had big discussions on the different issues, environmental issues, financial issues, but now we are building it. So, but it takes a long time, especially because in Austria the population has a good right to talk with the engineers. And if you don't, let's say, fully agree or do what the population says, you will get a major problem there. Yeah, this is the rule how we live there. All kinds of geological and geotechnical tests were done, and this is now the alignment. One could ask, why don't they go from this portal to this portal in a straight line? Yeah, the main reason is we have to keep it very flat, one point. And there are water reservoirs in this area where the population refused no way to pass here through this area in this region, because a lot of water could be, let's say, go down and then they lose the water in this area. So as you see the portal location on the eastern side, then we have intermediate construction lot which starts here. It's more or less a mining situation, because we have to make a tunnel for 1.4 kilometer in here, and then a so-called blind shaft for 250 meters going down here. And then we come to this situation where we need a ventilation shaft, and then we have a Fröschnitzgraben, which is a 450 meter deep shaft, 2 times 450 meter, which we will need at the end for the ventilation, but for the moment for the construction sequences. And then we have Krautschenhof. There's another solution now found, because this was too difficult to be built. There's another shaft done here in Sommerau. And then we are going out to Metzzuschlag. Here we have the train station. There's no way to start from here, the full tunnel construction, so it was decided to start from here, and from here. These are the, and also from Gloggnitz, of course. Now the question is always the time schedule, when will we be ready? I can tell you the environmental law and the other law stopped us already for 1 year again. The approval was taken away once again because we had some problems with the law. So I don't want to say we are ready at this date. We were thinking 1 year before. 2024 will be the date when we are ready. The date was already shifted for 1 year now, so we hope to be ready in 2025. And the 3 construction lots are these ones. You see there's an overlap. Our tenders are normally done in a way that there's no fixed border in it. It depends if these, let's say, construction companies are faster, then they are allowed to go into lot C. If they are faster, then they are allowed to go into this area. Same situation here. This makes a kind of competition between the construction companies or the different lots, which is quite good from our point of view. The question is, which construction technologies will we use for the different areas? You see, we are Austrians, we have a Swiss colleague who will not agree on the wording, but however, we call it DVM, TBM tunnel boring machines is the expression, and NATM, New Austrian Tunneling Method, and we have these sections to be built in NATM because there is, let's say, very loose ground in it. Then another part with NATM for the shaft. There could be some TBM in here, but the length is much too short, so at the end this will be done by NATM. And then there's a quite long section for TBMs, and also here for TBMs. There is a doubt from the construction company side already that they say, to shift down the machine for 450 meters, and assembling the machine down there is quite complicated, so let's do that by conventional or NATM methodology is under discussion. And also here we have some NATM sections. So it's a combination of two methods which will be used there. Typical cross-section, as you can see, is a drained cross-section. So we will level down the groundwater to the tunnel level. In the TBM tunnel, a double shell construction with a ceiling in between with drainage pipes there. In the conventional, a little bit smaller from the cross-section. In the areas where we have big water problems, we will do a very small tunnel in front, which allows to do injections for the full profile, which comes then later on. You see here a longitudinal section for the injection of the material, and then we come with the full profile running through the already injected material. To be able not to lose too much water. This is the main reason. It's an environmental issue to do it in this way. Third project, core-arm tunnel. Length, as I said, 33 kilometers. All of them have the duty to be able to run the trains with more than 200 kilometers an hour. This is the main goal. Gradient here, as I said, about 0.8, even lower percent. What is the sense? We are connecting the capital city of Graz to the capital city of Klagenfurt. This is a complete new railway line. There was nothing before, because people who wanted to go from here to there, they had to go up to a city down there and then go a very slow line down here. And this takes you about 3 hours. And this will then afterwards take you about 1 hour. Very new line. You see some pictures already from the construction from the open tracks. Again, we had to do a lot of exploration. Even this tunnel, from the geological point of view, is a little bit more easy than the Semmering base tunnel, I would say. You see the numbers of, let's say, boreholes and samples which were done here. Small picture from the starting points of this tunnel. We have one portal location on this side, one portal location on this side. In this area, the TBM will be assembled afterwards. This is a picture from the exploration phase, which was done first. And what you can see is that we have very shallow overburden at the starting points, but we get very high overburden up to 900 meters in the middle of the tunnel. There were some shafts to be built, 125 meters deep on the Carinthian side for exploration reasons, and also 48 square meter big exploration tunnels to get a knowledge of this geological behavior before we order a tunnel boring machine or before we fix how to build the big profile then afterwards. Yesterday we were speaking a little bit about squeezing ground, or let's say high deformable ground conditions. I explained the yielding elements, and this was to be found out during the exploration. Do we get very high deformations in the profile? If yes, then we should use such elements not to destroy the shotcrete shell. You see that a little bit more in detail. These are elements who can deform before destroying the shotcrete shells. We call them yielding elements. From the bird's view, you can see an overview here. So we have to pass the so-called core Alpe with on the main length of this tunnel. Here we have the shallow overburden, and also here shallow overburden. But in the middle we have an overburden of about 900 meters. Here very shallow, here very shallow. From the geology we have a neogene, which is a kind of siltstone, and in the middle we have this gneiss, the mica schist and the amphiboliths, and on the other side again the sandstone and the siltstone. We split it in 3 lots, cut 1, cut 2 and cut 3. So 3 different construction companies will be working from that. These projects are also good for the university because we developed a so-called cutter force measurement system together with geodata in a research project where you can now measure the forces directly on the disks and see that on the, let's say here is a test, of course. He is then the driver of the machine sitting 150 meters behind. And you can read out the forces on each of these disks, and this should give you information about the geology which you meet in front, which we hadn't up to now. The result is a typical one where you can see the red color here gives you an impression of very high loads, and the yellow or even white is very low forces on the machine, which gives you an information by overlaying this with the sketch of the geologist. Does it fit, yes or no? For us, this was a test. Does this system really work good? The really new knowledge was that we get forces which are higher than the disks were dimensioned for. Because a 17-inch disc on a tunnel boring machine has a maximum force normally of 250 kilonewton. And what we found out is, we get much higher forces on the disks. This was an interesting result. The other thing which we developed is a phase monitoring so that you can watch out of this tunnel boring machine and watch the phase in front of the machine. This development is still under development and is, I think, also an interesting issue because if we install more cameras, we get a full picture of the phase in front of the machine. Could support these geologists in future in a good way. And we did some reuse project, was mentioned yesterday by Gerard. We did a European project in how to reuse the material from a tunnel in a best way, not to produce any waste in future. We have the problem, we have very little space available in the European area, and we have to reuse this material as fast as possible. So we automated many things on the machine to measure the grain size, the grain shape, the chemistry, and we say we can do all the recycling on the machine because our tunnel is, let's say, 20 kilometers long, one lot is 10 kilometers long. We have enough space available to recycle it underground, not to use so much space outside. This is a typical sketch of the Coram tunnel. You see construction lot on the Styrian side, with the shaft Leibenfeld and the shaft from this side. We were not allowed really to start the construction works from here because there's a city or village, let's say, on this side. So the construction works start from this side and from this side. With a shaft, construction shaft, the tunnels will go this way, and the tunnel boring machines are lifted down through this shaft and and operate in this way. 60-meter deep shaft, as you can see, about 40 meters times 20 meters big shaft, and this is our construction shaft. Typical picture from that. And I would like to show you a film now about this Coram tunnel installation of the tunnel boring machines, which we tried to get in the Spanish language, and I hope it works.
Cartografía geológica extensa, perforaciones, estudios geofísicos y un túnel exploratorio proporcionaron datos precisos sobre la estructura geológica de la montaña. En 2008 se efectuó la palada con motivo de los trabajos preparatorios de construcción del túnel Koralm. 2 años más tarde se celebró el acto de colocación de primera piedra en el portal este. El avance se realizó en los primeros kilómetros siguiendo el NATM, nuevo método austriaco, un método probado a nivel mundial durante más de 50 años. La roca se rompe por medio de voladura o con excavadora. Para asegurar la cavidad del túnel se aplica hormigón proyectado. Las deformaciones de la cavidad son observadas con técnicas métricas. Con este método constructivo se crearon los tubos del túnel desde Frauenthal hasta la obra principal en Deutschlandsberg Leibenfeld, así como los primeros 1,7 kilómetros de la segunda y más larga parte de la obra. Para la mayor parte del trazado, solo se utilizarán enormes tuneladoras. Estas pueden lograr longitudes de avance diarias 2 o 3 veces mayores que las alcanzadas con el avance cíclico.
Etwa ein Drittel der Länge wird ja konventionell nach der neuen österreichischen Tunnelbauweise vorgetrieben, aber große Teile, vor allem des harten Kernbereiches der Choralpe, werden aufgrund der günstigen geologischen Gegebenheiten, aber letztendlich auch aufgrund der großen Vortriebslängen mit Tunnelvortriebsmaschinen vorgetrieben. Das ist für unser Projekt jedenfalls die wirtschaftlichere Lösung.
Mientras la tuneladora excava la roca, se revisten las paredes del túnel con piezas de hormigón prefabricadas. Esto proporciona así un gran ahorro de tiempo comparado con el avance convencional y además una medida de seguridad adicional. La tuneladora recorrerá un promedio de 25 metros al día, siendo posible un rendimiento máximo de hasta 50 metros.
Wir haben ja hier 2 Maschinen im Einsatz. Die erste Maschine wird 17 Kilometer Vortrieb machen müssen bis zum Endpunkt. Die zweite Maschine 14 Kilometer. Und vergleichbare Projekte in Europa, auch international, haben meistens ein Ende irgendwo bei 12 Kilometer gehabt.
Más de 500 empresas repartidas por todo el mundo fabricaron las piezas para las tuneladoras. Los componentes básicos procedían de Europa. Grandes piezas constructivas de acero fueron transportadas por barco desde Asia. Una nave de fábrica en Maribor, Eslovenia, ofreció las dimensiones apropiadas para el montaje experimental de la primera máquina tuneladora. Esta fue construida durante 4 meses para ser técnicamente aceptada en 2 días, habiendo sido puesta a prueba de pies a cabeza. Para su transporte a Austria, tuvo que ser posteriormente desmontada de nuevo. Miles de piezas fueron llevadas a Deutschlandswerk. Todos los componentes tuvieron que ser elevados para ser introducidos por el pozo vertical de 60 metros de profundidad. Después fueron transportados con el tren minero hasta la caverna de montaje a través de los 1,7 kilómetros de túnel ya existentes. Bajo tierra, las 2 tuneladoras fueron preparadas para su funcionamiento. Cada una pesa 2.000 toneladas y tiene 180 metros de longitud. Las 2 tuneladoras, bautizadas por los niños como Coral Mauli 1 y Coral Mauli 2, excavan la roca centímetro a centímetro. Estas gigantescas fábricas de túnel subterráneas, un símbolo de la más innovadora maestría austriaca en cuanto a construcción de túneles, estarán en funcionamiento 4 años en Estiria hasta que tenga lugar el encuentro de ambos tubos en Carintia. A principios de 2017 se llevará a cabo la construcción interior. Se ubicarán las vías y el túnel será técnicamente equipado. La luz al final del túnel la verán los pasajeros ferroviarios en el año 2023. Entonces, el transporte de pasajeros se hará a velocidad punta de más de 200 km por hora a través de la cordillera Choralpe, habiéndose consumado así uno de los proyectos del siglo.
Yeah, ladies and gentlemen, I hope I could give you a small overview about the actual construction lots in Austria, and that was my presentation. Thanks for your attention.